Hi, welcome to this module, and this module is the last module for our class 12, which is oscillators and noise, right. So, until now what we have seen? We have seen what are the oscillators. So, let us quickly recall what are the oscillators and what are the kind of oscillators, and then we will move to the noise. Okay. This is a second last lecture for this particular course. Next lecture we will see the data sheet, and finally we will have a recall lecture, okay, followed by some experiments. So, if you recall what are the oscillators, we know that oscillators require two things, which is called Bar-Khursan criteria. The first one is that the small signal which is the output, which is fed from the output back to the input, it should be in phase with respect to the input signal, right. That is first thing, that is the if the input signal is at 0 degree, the output signal which is fed back to the input through the feedback network should also be at 0 degree. The second condition was that the mode of A into beta should be greater than or equal to 1. What is A? A is your gain and beta is your feedback network, right. So, using this, if we use R and C as a feedback network, right, then we can use, or we can design oscillators which can be used for at lower frequency. While if I use L and C, that is inductor and capacitance as reactances or reactive components, then we can design oscillators which can work at higher frequencies, right. This is what we have seen. We have then seen what are the crystal oscillators, and what are the kind of crystal oscillators that can be used. We have also seen how the stability factor affects the crystal oscillator, as well as we have, if you recall quickly, Hartley oscillator, this we have seen, right, crystal oscillators we have seen. Then we have seen UJT oscillators and its characteristics curve, right. Now, let us see what is noise. Okay. What is noise? So, noise, when you talk about noise, it is a random fluctuation in an electrical signal. Noise in electronic devices varies greatly, as it can be produced by several different effects. Noise in fundamental parameter to be considered in electronic design, it typically limits the overall performance of the system. So, you see a signal, if I want a clean signal, right, if I have the distortion in the signal, right, that may be due to the random fluctuation of the electrical signal, and this random fluctuation of the electrical signal is nothing but your called noise, all right. This random fluctuation is called noise, and it can be produced by several different effects, right. We will see in the next slides what are the several effects, or what are the kind of noise that can arise in an electronic system. It is a fundamental parameter to be considered, because we have to remove this noise to obtain the pure signal, right. We have to remove the unwanted fluctuation in the signal, so that we can retrieve the wanted signal. Now, in general, the noise is also created by several components. You see here, chopper, noise of a car, siren, right, guitar, radio, ambulance, racing car, and what not, right. But this is unwanted signal for the earth, is called noise pollution, right. It is called noise pollution. Similarly, a noise for one person cannot be can be a entertainment for other person, all right. If you see this particular image, which is a very nice image, it was from enterprises-regulators.com, and we see that signal to noise, the sound that comes out of this particular radio, right, is a music for this guy, while it is a noise for this woman, right. So, you see, noise in any case can be defined in a different way, in a comic way as well, but when we talk about electronics, we are not talking about just a noise that we can hear, but noise that are present in the electrical signals. So, this is not some not noise which is a horn noise, or which is a chopper noise, or which is some honking, right, or which is some loudspeaker, or very loud music, but these are the noises which are present in the electronic form. And when this is a noise, right, and let us say if there are 100 people around me, it is all talking, then you may not understand what I am talking. You have to understand what is the signal. Suppose whatever I am right now teaching you is a signal, right, and then there are 100 people around me who are talking. So, it is difficult for you to retrieve the signal from, if I say that the 100 people talking is a noise, and what I am teaching you right now is a signal, then you have to retrieve this signal from the noise, right. That means, you have to filter out this noise and retrieve only the signal, so that you can hear it clearly, right. So, this is just an example. So, if you recall what we have seen earlier, we have seen signal to noise ratio, and what was that topic? The topic was CMRR, right. So, what is CMRR? CMRR is common mode rejection ratio, right. Higher CMRR, better the performance. Higher signal to noise ratio, better the performance of the electronic circuit. All right. So, in theory, or quickly, if we want to define noise, then you can say that noise is nothing but a random fluctuation in an electrical signal. All right. Let us now see what are the kind of electrical signals, what are the kind of noise present in the electrical signal. So, if you see the slide, what you see, that noise is purely random signal. The instantaneous value or a phase of waveform cannot be predicted any time. Now, what are external and internal noise? You see, external noise, internal noise. So, noise can either be generated internally in the op amp from its associated passive components, or superimposed by circuit by the external sources. So, the noise can be generated with the help by resistive components in the operational amplifier, or it can be superimposed when you design the different kind of circuit using external sources. External refers to noise present in the signal being applied to the circuit, or to the noise introduced in circuit by another means, such as conducted on system ground, or received one of the many antennas from by the traces and components in the system. So, let us not make our life difficult. The noise, so suppose let us say you have this circuit, okay, you have this op amp base circuit, you are introducing a signal from function generator or from function generator, right. You are introducing a signal from a function generator to the op amp circuit. Then this signal that is generated from this external source may introduce a noise in this circuit, Op amp itself may have noise generated by the associated passive components, but there is a possibility of external noise that comes out of the function generator and is introduced to the op amp. All right. So, that is something that we need to take care, we need to understand. Now, when you talk about types of internal noise, then there are several type of internal noise. We will just understand the definition, and we will just see one example to understand the noise. When you talk about internal noises, there are thermal noise, short noise, flicker noise, burst noise, and avalanche noise. All right. So, some or all of these noises may be present in the design, presenting a noise spectrum unique to the system. It is not possible in most of the cases to separate the effects, but knowing general causes may help the designer optimize the design, minimizing noise, in particular bandwidth of interest. So, all this noise may be present in the system, and it may not be possible to remove the effect that is caused because separate the effect of the noise on the system. But if we know that these are the noises possibly present in the system, at least in the band of interest, right. We have seen filters, and let us say this is a band pass filter, this is a band of our interest, correct, this is band of our interest. So, at least in this particular band we can optimize the design such a way that the noise is minimum, minimum, right. So, this is just again an example that at least minimizing the designer, right, who is designer, circuit designer can optimize the design such that the noise is minimized. So, let us see what are the type of noises. The first noise is thermal noise. So, this noise is generated by random thermal motion of charge carriers, usually electrons, inside an electrical conductor. It happens regardless of any applied voltage. That means that you see motion at absolute 0, slight heating will cause random fluctuation or motion of the electrons, and if I apply more heat, then it becomes even more random. So, this random motion of the electron or the charges would cause a noise. Okay. Now, power density is nearly equal throughout the frequency spectrum, approximately the white noise. The RMS voltage due to thermal noise generated in resistance R over a bandwidth delta F is given by this equation. You have to understand, or you have to remember this equation. We are not deriving this equation, but at least you have to remember this equation. Okay. So, noise voltage is equal to under root of 4 kb TR into delta F, where the noise from a resistor is proportional to its resistance and the temperature, and lowering the resistance values also reduces the thermal noise. So, when you talk about thermal noise, right, it is noise created by the motion of the carriers. Second is, if you increase the heat more or increase the temperature, the noise will increase. If the resistance value is higher, noise will increase. Lowering the resistance values will also reduce the thermal noise. Alright, and then you have to remember this equation. Now, let us see about example of a thermal noise. So, if I am given an example such that calculate the thermal noise at room temperature for a bandwidth of 1 hertz and impedance of 50 ohm. This is the question, this is a problem given to us. So, let us see how we can find the solution. We know that the thermal noise voltage is given by V equals to under root of 4 k TBR, where K is Boltzmann constant, T is 300 Kelvin, B is 1 hertz, R is 50 ohms, right. This is given, right, 1 hertz is given, 50 ohm is given, we should know what is Boltzmann constant. Okay. And we said room temperature we consider as 27 degree. So, 300 Kelvin. Therefore, the noise voltage is nothing but under root of, it is under root, okay, under root whole. So, if you do not have to use this symbol like this, if you just write under root or just under root like this and then write xyz value, that is consider that it is equivalent to xyz. Alright. So, when you see this symbol here, right, this is under root. Okay. So, under root of what 4. So, 4 is there into K is Boltzmann constant, into temperature in Kelvin, into bandwidth, into resistance, right. See here 4 K Boltzmann constant, temperature, bandwidth, resistance, correct. So, if I apply this, if I write these values, I can find out the noise voltage, which is 0.4455, right. That is the thermal noise that is generated because in this particular problem. Okay. So, this is an example of thermal noise. Now, let us see another noise called short noise. So, what is short noise? The name short noise is short of Schottky noise, also called quantum noise. Okay. So, short noise is also called Schottky noise or short form of Schottky noise, it is also called quantum. It is caused by random fluctuations in the motion of charge carriers in a conductor. You see potential force from the junction, potential from the junction, if there is N and P, then what will happen? There is a random fluctuation in the motion of the charge carriers. This random fluctuation of the motion of charge carriers in the conductor, right, N is electrons, P are holes. So, what happens that when there are random fluctuation in the motion, this will cause the short noise. Short noise is always associated with current flow. Okay. And it stops when the current flow stops. So, it is not like thermal noise that it is there even when we do not apply any current, right. It is just thermal noise is proportional to the temperature also, but short noise only comes into effect when there is a flow of current. Short noise is independent of temperature. Short noise is spectrally flat or has a uniform power density, meaning that when plotted versus frequency, it has a constant value. So, when you plot a short noise against frequency, you will find it as a constant value. Okay. Next is short noise is present in any conductor. Alright, short noise is present in any conductor. So, that is very important to remember. Let us see next one, which is our flicker noise, and then we will see burst noise. So, what is flicker noise? You see flicker noise. Flicker noise also called 1 by f noise. Its origin is one of the oldest unsolved problem in physics. You see from where it originates, we do not know. It is present in all active and passive components. It may be related to imperfection in the crystalline structure of semiconductors, as better processing can reduce it. So, what does that mean? That when we have seen what is imperfect crystalline structure, the crystalline structure, let us say in silicon we have seen 100, it is orientation, right, crystalline structure, but how the crystalline structures are, if there is an imperfection in crystalline structure, then it may cause, it may, we do not know, but this is just a theory, right, it may cause the generation of flicker noise. But the better processing of the material by reducing the crystalline structure or imperfection in the crystalline structure would reduce the flicker noise. Okay, would reduce the flicker noise. This is what we are assuming. So, what are some characteristics of flicker noise? So, flicker noise, it increases as frequency decreases, right. See, because what we have found is when you increase the frequency, the flicker noise decreases. On increasing the frequency, the flicker noise decreases, right. That is why the name is given 1 by f noise. You see here 1 by f noise. It is associated with a DC current in electronic devices. It has same power content in an octave or in each octave or decade, right. Let us see next one, which is burst noise. What is burst noise? Burst noise consists of sudden step like transition between two or more levels. It is related to imperfection in semiconductor material and heavy ion implants. When there is a heavy ion implantation, you will see or you will find there is a burst noise as high as several hundred microvolts, lasts for several milliseconds. Burst noise makes a popping sound at rates below 100 hertz. You see, that is why it looks like a burst, alright, it makes a popping sound. When played through a speaker, it sounds like popcorn popping and hence so called popcorn noise, alright. So, it is related to imperfection in semiconductor, it has and heavy ion implants, right. It is a sudden step like transition and the voltage is as high as 100 microvolts, last for several milliseconds. So, when you connect a speaker and you will hear a popping sound at rate below 100 hertz, below frequency of 100 hertz, and because of its sound similar to a popcorn popping, it is also called popcorn noise. It is also called popcorn noise. Low burst noise is achieved by using clean device processing and therefore is beyond control of the designer. Okay. That is about the burst noise. Now, let us see one more kind of noise, which is your avalanche noise. So, what is avalanche noise? Avalanche noise is created when a PN junction is operated in the reverse breakdown model. Alright, when is operated in reverse breakdown model. So, what happens under the influence of strong reverse electric field with the junction depletion region, electrons have enough kinetic energy, they collide with atoms of the crystal lattice to form additional electron pair. You see, when you deplete the region, the electron would have enough kinetic energy and it will collide with crystals. As you can see, it is colliding here with crystals and dislodging the electrons, further electrons, right, and forms additional electron hole pair. These collisions are purely random, produce random current pulses similar to short noise, but much more intense. Okay. When electrons and holes in depletion region of reverse bias junction acquire enough energy to cause avalanche effect, a random series of large noise spikes will be generated. The magnitude of noise is difficult to predict due to dependency on the material. So, more or less you see what we have found, more or less it depends on the semiconductor material, it depends on the type of material, because it has to depend on the material. Only the thermal noise in particular we have seen that depends on the temperature, right, it depends on the temperature. And rest we have seen short noise, we have seen the burst noise, we have seen the popcorn noise, we have seen the avalanche noise, right. So, this will be the end of this particular lecture, which is our lecture number 12, oscillators and noise. Now, you guys, you had to understand, once you read what are the right types of noises, right, understand where exactly these noises are generated and how can you solve or how can you find if there is a noise in an electronic circuit. Okay. Do something, that is your homework, do something by yourself, understand how the noise is generated. All right. So, in the next class we will see quickly the data sheet of the operational amplifier, and we will see some of the parameters in the data sheet. Few of the parameters are already discussed in this entire course. You will find it when you open a data sheet, lot of parameters we have already discussed, which are mentioned in the data sheet. Few of the additional parameters we will discuss, and then we will have a last lecture, which will recall lecture, which will consist of whatever we have done from class 1 till now, but in a little bit faster mode, so that you kind of recall whatever we have done till now. All right. After that, we will have the experiment classes. After that, we will have experiment classes, where I will show you how to implement the circuit on the breadboard and how to use Simulink to solve some of the circuits. Okay, to apply some voltage. We will see, we will gather the components from the library, we will attach these components to form a circuit, we will apply a signal, and you will see what is the change in the output using the oscilloscope in Simulink, which is a simulation software. But we will also do the similar study using the breadboard, using the oscilloscope, frequency generator and DC power supply. Only 3 tool we will use, or 3 equipment we will use, and we will design several kind of circuits related to the operational amplifier. All right. So, till then you take care, read this particular lecture, and I will see you in the next lecture. Bye.